In this video, I want to talk about the difference amplifier circuit. So this is an example of a difference amplifier circuit. As you can see, we kind of have combined the two inverting amplifier circuit and the non-inverting amplifier circuit to come up with this circuit that we are seeing here. So again, we have the op amp connected here. The non-inverting input is signified with this plus sign. The inverting input is signified with this minus sign. We have now what we call RB that is connected between the output and the inverting input of the op amp. This is again the feedback resistor. Then the inverting input is connected to a voltage source, we call it here VA, through a resistor which its value is RA. As for the connections to the non-inverting input, we have RD to be connected between the non-inverting input and the common node or the ground. And then we have RC and another voltage source VB that is basic, that are in series, and then they also get connected to the ground. So now that we have this circuit, how can we come up with the equation for the relationship between VO and VA and VB? So like before, I write down the constraint that we have. So we have Vn equals Vp. So Vp is between the non-inverting node and the ground, and Vn is between the inverting node and the ground. And also we have In equals Ip equals 0. So we have In in this direction as it's shown here, and we have Ip again considered in the same direction. So we know that because of the high internal resistance of the op amp, these two are 0. So now that we have this, what we can do is that we can write down the node voltage equation for the inverting node, for the node that is connected to the inverting terminal of the op amp. So if I do that, we have Vn minus Va over Ra plus Vn minus Vo over Rb plus In equals 0. So right off the bat, we know that this is 0 because of the second constraint that we have. Based on the first constraint, we know that Vn equals Vp, but what is the voltage at the non-inverting node or the non-inverting input of the op amp? What you can do is that either you can write a KCL for this node, or you can simply just use a voltage divider analogy, because as you can see here, Ip is 0. So when Ip is 0, we have this voltage source which will be divided between these two resistors. So let me just do a KCL first. So this one is for the second node. If I go with the KCL, what I have is that Vp minus Vb over Rc plus Vp over Rd equals 0. So let me just add Ip as well, and then I eliminate it based on the second constraint. So that means that 1 over Rc plus 1 over Rd multiplied by Vp equals 1 over Rc Vb. So if I combine these two, I have Rc, Rd, and in the denominator will be RD plus RC. So that makes VP to be RD over RC plus RD multiplied by VB. So that is the conclusion that we get if we use the node voltage equation or the KCL equation at this node. But if you do the voltage divider too, you get the same result, because if you remember from before, when you have two resistors to be connected in series, first of all, the equivalent resistance is the sum of two, and second of all, if they are all connected in series with a voltage source, the voltage across each one of them is basically a ratio that is determined by the value of the resistor in question divided by the equivalent resistance multiplied by the input voltage. So we have basically VP again RD divided by equivalent resistance multiplied by VB. So using these two techniques, we basically get the same result. So we know this is VP, and also from the first constraint we know this is VN2, right? So now that we have this, we can replace it in the original equation. So anywhere we have Vn, we replace it with this equation. So we have RD over RC plus RD VB minus VA over RA plus RD over RC plus RD VB minus V0 over RB equals 0. So by doing some basic algebra, we can come up with the final equation that shows the relationship between VO and VA and VB. So after all these manipulations, VO is going to be RD multiplied by RA plus RB divided by RA multiplied by RC plus RD. That's multiplied by VB multiplied by RB over RA multiplied by VA. So this is the final equation that shows the relationship between VO, the output voltage, and the difference of VA and VB. So as you know, all the resistors that we are using here are positive resistors, right? So this ratio is positive, this ratio is positive. But because of the configuration of this circuit, we have this negative sign that basically calculates the subtraction between these two ratios. If I want to say it another way, VB is connected to the non-inverting input of the op-amp, which means that its gain is going to be positive, while VA is connected to the inverting input of the op-amp, which means its gain is going to be negative. So since we have a combination of these two positive and negative gains, this is what we have as the final result as a difference amplifier. So these are all the steps. The first one is again writing the KCL for this one. Using the voltage and current constraint, we can write down the equations for the current of the op-amp and also the voltage at the non-inverting input. Combine them all. we get to this final equation that helps us to understand what is the relationship between the output and the two inputs. But now what happens if you want this to be completely having the same scales? If you want both VB and VA having the same coefficients. So the answer to that is if you choose RA, RB, RC, and RD, so they can satisfy this equation. So if the ratio between RA and RB, is the same as the ratio between RC and RD, then this equation is simplified even more. So let's just do that. So considering this, VO becomes RA RD plus RB RD divided by RA RC plus RD. This is multiplied by VB minus RB over RA VA. So now if RA over RB equals RC over RD, that means that RA RD equals RB RC. So basically multiplying the numerator of the left hand side with the denominator of right hand side equals multiplication of the denominator of the left hand side multiplied by the numerator of the right hand side. So now if we do this, if I replace this based on this equation, VO becomes RBC plus RBD over RA multiplied by RC plus RD VB minus RB over RA VA. And now this one is RBRC, RBRD. So as you can see, RB is common between the two, so I can factor it out. So we have RB multiplied by RC plus RD divided by RA multiplied by RC plus RD VB minus RB over RA multiplied by VA. So as you can see, I can eliminate these two terms that are common between the numerator and the denominator. So the final result will be RB over RA multiplied by VB minus VA. As you can see, RB over RA multiplied by VB minus VA. So as you can see, we have RB over RA for both of these terms. So now if this condition is satisfied, so let me just put arrows here so you don't think of it as I said this is wrong. So if this condition is satisfied, that means that both VB and VA would have the same coefficients. And this is going to be a true difference amplifier with identical gains for both of the inputs. And that is the final conclusion, written much nicer. So in this video, we went over the circuit for the difference amplifier using an op-amp, and we learned how we can derive the equation that shows the relationship between the output and the difference of its two inputs.